Hello, welcome back. The title of this lesson is called Using the Fundamental Trig Identities. This is part 1. So in the last several lessons, we have introduced many different identities, and we've already proved many of these identities in their own separate lesson. What we're going to do in this lesson is we're going to use these identities in order to solve problems. So here's where we get the actual practice with using these identities. These are called the fundamental identities because as you go on through math and science and engineering, these identities are going to be used over and over again. I don't necessarily want you to memorize them. I'm just letting you know you'll see these a lot. So we have the reciprocal identities, and these come from what I call the trig rainbow. The definition of sine and its relation to cosecant. We went over all of this in the past, and you can draw this little rainbow to help you remember exactly all of these that I have written on the board here. Every one of these is just a reciprocal relationship. The even and odd identities, we already went through them before, and this has to do with if the sine and the cosine and the tangent function are even and odd. And we prove them by graphing those things, looking at the symmetry, and showing and convincing ourselves that these identities are true. And we've already gone over these identities. Next, we talked about the cofunction identities, in that you can rewrite a sine function in terms of a cosine. You can rewrite a cosine in terms of a sine. And the 90 degrees minus theta here, all of that was explained in a previous lesson where we derived all of these, and it has to do with shifting the sine and the cosine and the other functions left and right along the x-axis. And it turns out that the shape of the sine and the shape of the cosine are exactly the same shape, they're just shifted relative to each other. That's what these identities are kind of like putting down in mathematical form. So we've talked about and we proved all of these. Lastly, we proved these Pythagorean trig identities, which we use the unit circle and Pythagorean theorem to prove these. So once we have proven all of these, now again in this lesson, we just are going to use them. Now, when you solve problems in trig, they're never going to tell you which identity to use. What you need to do is be familiar with all of the identities. You don't have to memorize them all, but you have to be familiar with them so that as we solve our problems, you will know what is in your tool bag. And this is how we get practice. So let's go ahead and tackle problem number 1. It's simply to simplify. Remember back to 4th or 5th grade when you're simplifying fractions. We just say simplify the fraction. Well, in trig here now, we're going to be simplifying the following function. Sine of the angle theta multiplied by secant of the angle theta. Now, before we do anything else, I want to point something out. What this is saying is the sine of theta is multiplied by the secant of theta. It's like there's invisible parentheses around this term and then invisible parentheses around this term. The way you would calculate this is once you were given an angle theta, let's say you had 45 degrees, you would take the sine of 45, then you would take the secant of 45, you would get those two answers, and then lastly, you would multiply them together. Because order of operations, you learned order of operations a long time ago in math, but now that you know the trig functions, basically the order of operations is such that the trigonometric functions are evaluated very high up in the order of operations. So you evaluate the secant and the sine, you get the results, you multiply them together. So what we want to do is simplify this into a simpler form that calculates the same exact answer. Now, I haven't told you what to do. So you have complete freedom in what to do. In fact, you can do anything you want as long as what you're doing is legal. Everything on these boards with all of these identities, they're all legal. So you can substitute any of those. And of course, you can add fractions and you can divide fractions. You can do all of the lower level math that you know as well. So my advice to you is when you're proving something or simplifying something involving trig functions, it's very likely that you don't know ahead of time how to get to the answer. Like, I know this because I've done it so much, but when you see it the first time, you probably aren't going to know exactly how to get all the way to the answer in your head. That's normal. Don't try to get all the way to the answer. Don't try to chart a path or a course all the way to the answer in your head. It's not going to work. For simple problems, it might work, but it won't work in a minute when I give you something more complex. Instead, pick something that you think is reasonable, that you know is legal, and then take that first step and see if it gets you closer. So when I look at sine and secant, I know that sine is sort of like a fundamental trig function, but the secant is actually kind of derived from the other ones. And I remember that, and we talked about that. Now you can memorize this list if you want as the secant is 1 over the cosine, but I taught you to use this trig rainbow here. And so the way you do it, I'm just going to literally show you how I would solve this myself, is I go off to the side and I say, well, how do I want to rewrite the secant? And I write all my trig functions in this order: sine, then cosine, then tangent, then cotangent, then secant, cosecant. Now you do have to remember this order: sine, cosine, tangent, then cotangent, then secant, cosecant. And what you do then is you basically connect them in a rainbow like this, but I'm interested in the secant. The secant goes with the cosine. The other ones are joined up like this as well. And what this tells me is that the secant is equal to 1 over the cosine. The cosine is also equal to 1 over the secant. So this rainbow thing, it's basically an easy way to remember all of these identities, essentially, is what it is. And so that's the way I want to tell you to do that. So what I'm going to say for the next step is that sine of theta is here, but I'm going to multiply that by secant, which I now know from this is 1 divided by cosine, 1 over cosine of theta. Now I put a dot here, whereas there wasn't not a dot in the beginning, only because I have a fraction and I'm more comfortable putting the multiplication symbol there as well. All right, because I know that this sine is like sine over 1, and so I can multiply fractions. How do I multiply fractions? I multiply the numerators and I multiply the denominators. So sine of theta times 1 is this, and on the bottom there's an invisible 1 in the denominator times cosine theta right here. And so then I ask myself, okay, so this is simplified down to sine theta divided by cosine theta. Does that sound familiar? And the answer is, you should memorize this one. This is one we use a lot. Tangent of an angle is sine theta divided by cosine theta, whereas the cotangent is reversed, cosine over sine. That is one that you will have to remember. I promise it will become second nature. So this is equal to the tangent of theta. All right, this is the simplification of this. And I think everyone would agree that this looks simpler than where we started. What this is saying is if I get a calculator and I put an angle in here, let's say 90 degrees, or let's pick 88 degrees, and I take the sine of 88 degrees, and then I take the secant of 88 degrees. I get those two numbers and I multiply them. I'm going to get some answer, okay? And then separately, if I put 88 degrees here and take the tangent, I'm going to get some answer. The two answers I get will be the same, because what I am saying is that since I have a logical set of steps getting from here to here, that anywhere I see sine theta times secant theta, I can essentially replace it with this because these are equivalent statements. It's just that this one is a little simpler. It's just like 5/10 of a pizza means I have 5 out of 10 slices. But you all know that if you have 5 out of 10 slices, it's the same thing as 1/2 of the pizza. So 5/10 looks different on paper than 1/2, but actually they represent the same thing. So these statements look different, but they are the same thing. If you were to graph this function, if you just stick this into a graphing calculator and then separately stick this in a graphing calculator, the graphs would look the same because they are identical statements. They just look a little bit different. All right, let's tackle problem number 2. So I'll just go right under here and we'll take a look at problem number 2. We want to simplify the following: tangent of x divided by sine of x. Now, before we actually do anything with this, notice that here tangent is operating on something I'm calling x, and sine is operating on something I'm calling x. X is an angle in degrees or in radians. But then up here, I'm using a letter theta. Okay, you see, these are just variables. X is a variable. Theta is a variable. It just happens to be a Greek letter. Don't get so wrapped up in what variable is being used. Anything that a sine or a cosine or a tangent operates on is going to have some letter, but it's basically a placeholder for an angle. They always operate on angles. So sometimes you'll see x's, that just means some unknown angle x. Sometimes you'll see theta, that just means an unknown angle theta. Oftentimes later we'll use alpha. This is the Greek letter alpha. Sometimes I'll use the letter beta, which is a B with a little tail at the end. Right? Later in calculus, you use, of course, we use theta all the time, but we also use another Greek letter called phi, which is a circle with a line down below. Don't get so worried about it. It's just a symbol. You got to break down the fear you have of these symbols. They're just symbols, okay? But they're just variable placeholders. Usually alpha, beta, theta, phi, they usually represent angles, but in trig, we often use the variable x. If your problem has x's, you carry it through with x's. If it has thetas, you carry it through with thetas. But ultimately, it means the same thing. It's just a variable that represents an angle. Now, what do you think you do here? All right, we need to simplify this. I don't know of a great way to turn the sine into something simpler. I mean, of course, I could turn it into a cosecant, but that's not really any simpler. Cosecant's actually a little more obscure than sine. So I want to leave this alone. But the tangent, we already know I can turn that into something a little bit simpler. Tangent is equal to the sine divided by the cosine. But that whole quantity, tangent, is divided itself by something on the bottom, which was sine of x. But because I'm going to end up having to manipulate this as a fraction division, the sine of x on the bottom, I'm going to write it as sine of x over 1. Because this is equal to sine of x. Anything over number 1 is the thing itself. And the reason I'm writing it like this is because I'm going to have sine of x over cosine of x. Look, I forgot my x right here. Sorry about that. And this division of a fraction will be changed to multiplication, and the bottom fraction will be flipped over and multiplied 1 over sine of x. So notice how we're using things that we've learned in lower level math. What I'm doing when I change it to multiplication and flipping it over and multiplying, I'm just doing fraction division. It's exactly the same thing that you learn, in 4th or 5th grade, 3/4, divided by, 2/6. Or you could write it as 3/4 with a long division bar, 2/6. What you do is you change this to multiplication, then you flip it over and you multiply. So all fraction division turns into multiplication. We just applied that to a little more complicated looking thing, but that's all that we're doing. Divide and then flip and multiply. All right, now notice what we have though. We have a sign on the top and a sign on the bottom. And just like numbers, sine of this, whatever the angle is going to give me a number back. Sine of the same angle will give me the same number. So I can strike through it and cancel it because they're essentially dividing. Just like when you have, 2/6 multiplied by, 5/2. The 2 on the top and the bottom, you can cancel through them because they're essentially dividing away, giving you 1. And all I have left now is 1 over cosine of x. All right, now I can leave it like this if I want to, but if I'm trying to get it into the simplest form possible, then I remember from my rainbow, my trig rainbow, that cosine here is linked with secant. This means that secant is 1 over the cosine, but I already have 1 over cosine, so this is just the secant of the variable x. And I think we would all agree that secant of x is looking simpler than tangent x divided by sine of x. But what it means is if I put an angle in here, 10 degrees, take tangent of 10 degrees to get the answer, take sine of 10 degrees, get the answer, and then divide them, then I'll get a final result. If I put 10 degrees into the secant and calculate it, that final result will match what I calculated before. Even though the math looks different, the expressions look different, they give the same result. That's why we have equal signs everywhere. All right, so here we have, and notice, by the way, that we've done a lot of work, and we did refer back, here a little bit, but mostly we didn't. Mostly I just referred back to this trig rainbow. This is how I want you to do it on your paper. That's how you're going to remember this. All right, let's take a look at something a little more complicated. What about 1 minus the sine of theta multiplied by 1 plus the sine of theta? All right, when students look at this, immediately, a lot of times alarm bells go off, woo, 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 very, very complicated. Okay, take a deep breath. How would you handle this if it was just algebra? Like if I gave you a different question, and if it was like 1 minus x, and then it was like 1 plus x, what would you do? Well, you learned in algebra, you do FOIL, right? The first terms multiplied, the outside terms, the inside terms, the last terms. That's what you do. You do the same thing here. So just because there's trig functions involved, you still have to follow the rules of algebra. You have a binomial, which means 2 terms, multiplied by another binomial, which is 2 more terms. You have to multiply them the same way. So that is exactly what we're going to do. So for the next step, the first 2 terms multiplied, 1 times 1 there, is going to give you 1 squared. So I'm going to write it as 1 squared. Even though I know the answer is 1, I'm going to do that there. The outside terms is going to be 1 here times sine. Don't worry about this minus sign. That is attached to this term. 1 times the sine of theta, which means I'm going to have the sine of theta here. The inside terms, 1 times the negative sine is going to give me negative sine of theta. And then the last terms, I have a sine times a sine, but this one's negative and this one's positive. So it's negative sine squared theta, because the sine times the sine is this, and the negative times the positive is this. And so this looks ugly, I agree with you, but this is exactly what this multiplication is. But notice what happens. the inner terms cancel because the sine of theta subtracted with the sine of theta gives you 0. Because remember, theta is just a placeholder for an angle, any angle. If I put 60 degrees in here, then I'll have sine of 60, which will be a number, sine of 60, which would be a number, and they'll subtract away, giving 0. So I can strike it through no matter what angle actually is the angle, it will always cancel out. And so what I'm going to be left with is the following. 1 squared, all this is gone now, this minus sign is still here, sine squared theta. Now at this point, you are patting yourself on the back because you are thinking, I'm done, it looks simpler. I mean, I think it looks a little simpler than that, and you think, great. But in trig, I want you to always take a look at your answer and see if there's any way that you can get a little bit simpler still. And I'm going to tell you right now in the beginning that you might not see how to simplify something the first time all the way. But as you get more practice, you will start to see these patterns. Most people that see this the first time think that we're done and we can't do anything else because it's not obvious what to do. But when I show you what to do, you'll be like, oh, but some people will say, well, I wouldn't have noticed that, or I would never have gotten that. But, you know, math is all about learning by example. You've seen it now and you will recognize it for the next time. We all learn like this. The first time I saw this, I didn't know what to do either, okay? Now it looks like there's nothing to do. Now this number 1, anytime you see a number 1, actually I'm going to rewrite this from the 1 squared. I'm just going to write it as 1 minus sine squared theta. All right? This number 1 is a clue. When you see the number 1, you need to think about any identity that you know that has the number 1 in there. Now there's ones here, but those aren't very helpful. But let's go back to these Pythagorean identities. Sine squared plus cosine squared is 1, and it looks like that isn't going to be very helpful here because you don't see this term anywhere. But I do see a number 1 over there. And that, again, you're not sure what to do, but just go over here to the side and write down. We know that the cosine squared of an angle plus the sine squared of an angle is equal to 1, right? We know that this is the case. So anywhere in a expression in trigonometry, anywhere you see the number 1, you can actually just replace it with this term. And this is going to be useful because we have a sine squared in our answer. So what I'm actually going to do in the next step, I'm going to take this number 1 and I'm going to replace it with this whole thing because these are equal. So it'll be cosine squared and then plus sine squared. But then this is still present, minus sine squared theta. Now don't forget, exactly what we did. Basically what we did is we said, all right, this, like this 1 is being replaced by this giant term. But notice what it has opened up for us. Because now we have a sine squared of theta minus a sine squared of theta, and these cancel away. Because no matter what theta is, if I calculate it, I'll get the same number subtracted away. And so the answer to this thing, the only thing left is cosine squared theta. And there isn't really a good way to get any simpler than that. If you try to write, and you could say, well, cosine theta is just 1 minus sine squared theta, but then you get back to where you started. That doesn't really help you. Okay, you can't really get any simpler than this. So again, the first time you see that, you might say, well, I never would have thought when I see a number 1 to replace it with that. Well, now you know. It's not like you're wrong or you're dumb because you didn't see it. None of us are born. Like when I was like 6 years old, I had no idea what sine and cosine were. Okay, none of us do. It's all about practice and it's all about recognizing patterns. And you don't get that from just watching a lesson. You get it from solving problems. I mean, you cannot go onto a basketball or a baseball field and be great at baseball or track or swimming or anything without a lot of practice. So as we do problems, you will see, oh, well, if there's a 1, okay, I know that I can replace it with this. Also, notice there's a 1 here. I could have moved this over. Secant squared minus tangent squared is also equal to 1, and I could have put that here. The problem is, it wouldn't have canceled with anything. So tangent squared and secant squared, they're not present, so that wouldn't have helped me. Cotangent squared, cosecant squared are not present, so that wouldn't have helped me. This one only helps me because the rest of the problem had something that canceled. All right, next problem. We're going to have cosine of an angle alpha times cosecant of an angle alpha times tangent of an angle alpha. Remember, I told you, don't get scared by symbols. Alpha is just a Greek letter. Beta is a Greek letter. Theta is a Greek letter. Phi is a Greek letter. This could be X, X, and X. It would be the same problem. It could be Y, Y, and Y. It could be A, B, 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 C, C, C. You get the idea. And you should practice writing your little alphas. It looks like a little fish like this, or a sideways ribbon like this. So what you need to do is think about, what can I replace? The cosine of theta is basically as simple as you can get, so I'm going to leave that alone. However, it's multiplied by the cosecant. What is the cosecant? Cosecant is 1 over the sine. I didn't have to refer back to my table of trig of identities, because I'm teaching you the way to remember them in real life. You don't look back on this chart, okay? I had to write it down for you, but I really want you to do this. I want you to say, okay, cosecant is 1 over sine. So I replace this with 1 over the sine of alpha. And this is basically that right there. But then I'm going to multiply it by the tangent. And I know that the tangent is the sine of the angle divided by the cosine of the angle. And this is here. So what I'm doing is replacing the cosecant with something else and the tangent with something else. And I'm hoping that something will cancel. Now, you may not see it ahead of time. It's okay, but you just do it and you try, okay? So notice I have a cosine on the top and I have a cosine on the bottom, because this is cosine over 1. So immediately I can cancel the cosine with the cosine. But then I notice, wait a minute, I have a sine on the bottom and a sine on the top. So these can cancel also. So you're thinking, well, what is left then? Because ultimately, remember, when you cancel things in math, they don't just disappear. When you cancel, they're really dividing away, giving you 1. The cosine is really being divided by this cosine, giving you 1. This sine here is being divided by this sine, giving you 1. So you replace everything with 1, and then all the ones multiply, and so really all you have left is the number 1, and this is the answer. So what does this mean? It means if I take the original expression and replace any angle I want in there, I'm going to get 1. Like if you put 52 degrees and take the cosine, 52 degrees, and take the cosecant, 52 degrees, and take the tangent. Get all those numbers and multiply it, you'll always get the number 1, no matter what the angle is. Because some of these things, they reduce down to simple numbers. All right, now I have a few more problems. I'm going to erase this board, and we're going to solve a few more to wrap up this lesson. All right, let's continue on. Let's do a different type of problem. What I want to do is I want you to write the function secant of theta in terms of only, and I'm going to underline the word only, sine of theta. So in other words, on the first line of the solution, we're going to write secant of theta. And I want to write secant of theta in terms of sine of theta, but only sine of theta. So the first thing you're going to do is you're going to go over here and rewrite your trig rainbow. Sine, cosine, tangent, then cotangent, then secant, then cosecant. And the secant is what I have here, so I'm going to connect the secant here. The secant is 1 over the cosine. Certainly that's not equal to sine, so that's not anything to do with the sine. And it's really not possible to turn a cosine directly into a sine. So it appears that you're completely basically busted right there, and you don't know what to do. So what you do in that situation is you take the only step that you can and just see if you can think of something else. You can't often think all the way to the answer. So I do know, though, that the secant here is 1 over the cosine. So 1 over cosine of theta. Now, the answer is in terms of cosine of theta. I want the answer in terms of sine of theta. Now, I lied a little bit a minute ago when I said you can't turn a cosine directly into a sine. What you need to do is think, what identity involves only sines and cosines? I'm going to say that again. What identity only involves sines and cosines? Now, there are some choices. Okay, you could go back through your list of identities, right? Yeah, this one involves sines and cosines, but it also involves tangent. So it doesn't let me turn a sine directly into a cosine without introducing something else, okay? You have these even and odd identities. This involves only sine and only cosine, so it doesn't involve both of them. I need an identity that's going to turn a sine into a cosine. So here's a sine going into a cosine. The problem is that it's got this 90 minus theta here in the cosine. And that is not at all present here. So in theory, you might think that you can use this to turn a cosine into a sine, but it's practically hard because inside of the cosine, there's all this junk that's not present in my original problem. So I go down. Eventually, I land on this one, which I told you in the beginning the sine squared plus cosine squared equals 1, the Pythagorean trig identity, is one of the granddaddy identities. We use it constantly. It involves only sine and cosine and a number, the number 1, and so I can turn a cosine into a sine, it turns out, even though in the beginning I said you couldn't. So let's see how we would actually do that. What you do is you go off to the side of your paper and you write down, okay, cosine squared of an angle plus sine squared of an angle is equal to 1. And what I want to do is I want to solve this for cosine and then stick it back in there. So if I solve for cosine squared, it's going to be 1 minus sine squared. All I did was subtract this from both sides. But this is cosine squared and this is cosine, so I need to take the square root of both sides. The cosine of the angle, if I take the square root of both sides, I got to add my plus or minus, and then it's going to be 1 minus sine squared of theta. So it turns out that you can turn a sine into a cosine. And the cosine of an angle is exactly equal to this, the plus or minus the square root of 1 minus sine squared of theta. All right? And so what I can do is I can put this in here. Right? And I can say that then finally it's going to be 1 over the cosine, which I've just defined as plus or minus square root 1 minus sine squared theta. Right? Plus or minus 1 over sine squared theta. And that is the answer to this guy. So I can turn a secant directly into this. So I've turned the cosine into this radical thing. And so since secant is 1 over the cosine, this is equivalent to this. Now, this is not any simpler than this. Okay, this is certainly a more complicated way to calculate the secant, but they're equivalent in the sense that I can, I've done what the problem says, write the secant in terms of only the sine. Now, of course, there's a number involved, but it doesn't. The numbers aren't a problem. It means only the function sine. That's the only trig function allowed in the answer, and so that's what we have here. So a little bit of a weird thing, but I wanted to do this problem because I wanted to show you that it doesn't always appear that you can do something, but if you find the right identity, then you can get there. That's what this is about. All right, next we have two proofs. One is easy, one is harder. Prove. They're both doable, okay? Don't worry about it too much. What I want you to do is prove that the sine squared of some angle x times 1 plus cotangent squared of x is equal to 1. Now this is a proof, and we've done some proofs before, but I'm going to reiterate as we do this here. When you prove something, we have an equal sign here, but really you cannot treat this as an equation that's already true. You can't, you can't like subtract and add numbers to both sides because that's an equation we know is true. We're trying to prove this is true, so we cannot assume it's true in order to prove it's true. You see what I mean? So what you can do, though, is you can work only on one side, or you can work only on the other side, or you can work on both sides in parallel independently to try to get them to equal. What we're going to do is focus on the left-hand side, the more complex side, and see if we can get it to equal 1. Now, if you can look at this and just see in your mind how it equals 1, then you're much, much smarter than me. So I cannot see these things. What I do is I try to find the first logical step, right? The first logical step. And sine squared is already a pretty simple trig function. I mean, it's squared, but I know I can rewrite it in terms of cosine if I really want to, but it's going to look ugly like this, so I don't want to make it more complex. So I'm not going to actually mess with anything on the outside. The logical thing to do to start with is this cotangent function, because cotangent, I should say tangent, is equal to the sine divided by the cosine, but the cotangent is equal to, of course, is equal to this also, cosine over sine. We don't want to write it in terms of a tangent because we want to introduce functions that it might be able to cancel later. So if we write it as cosine over sine, then we don't know, but at least we have a chance of canceling with this later. So we're going to write this as cosine squared over sine squared. Why squared? Well, because the cotangent was squared. So cotangent cosine over sine, the whole thing's squared, and so we have to do it. Now what I'm going to do is leave the right-hand side alone. I'm not going to touch it or anything else. I'm only kind of manipulating the left-hand side. Now what would we do next? We need to distribute the sign in. So what we're going to have when we take sine squared times 1 is sine squared of x. But then the plus sign, we have to multiply this in. Don't do too many things at once. We have a sine squared, and then this is a fraction cosine squared of x over sine squared of x. But you can see right away that, because this is like over 1 here, in the numerator we have a sine squared, and the denominator we have a sine squared, so they go away. So what do we have left? We only have sine squared plus here. These are gone now. We have cosine squared of x. Now, does this look familiar? We've been using it over and over again. Anytime in a trig expression, when you see sine squared plus cosine squared of the same angle, you just can replace it with a number 1. Okay? Now, this is a good example. Notice that this identity is written in terms of theta. But theta is just a placeholder for an angle. It doesn't matter if I use theta or alpha or beta or gamma or delta or buffaloes or apples. It doesn't matter what the placeholder is, as long as sine squared of the same thing, then you can replace it with the number 1. Here we have the variable x. This just means whatever x is, if I take the sine and take the cosine, square each of those answers and add them, then I will always get the number 1. And then since I only manipulated the left, the right-hand side stayed unchanged, then 1 is equal to 1, and the proof is verified. So you can kind of like circle this, or you could circle this, and you could say this is proved. Like this. Okay? So that is a relatively simple proof, but I just want to reiterate again that when you prove things, there's many paths to get to the answer. Real mathematical proofs by actual professional mathematicians are hundreds of pages long. These are simple proofs, but you still have latitude in the exact way that you get there. So in the next problem, which is our last problem, we're going to prove something more complex. I'm going to choose a path and I'm going to prove it to you. But when you solve it yourself, you might pick a slightly different path, and that's okay. It's just like solving equations. You can do different things to get to the same answer as long as they're all legal. So just keep in mind that your path might be different and probably will be different than mine. Here is our very last problem. Here we have tangent of theta plus cotangent of theta, and we're going to divide all of this by secant squared theta. And what I want to do, this is not a proof. What I want you to do is simplify this. Right, this is a simplification. So I lied a little bit. It's not a proof, but it's the same sort of thing. We want to simplify this. Now, there are many, many ways to tackle it. In fact, on my paper, I don't know if you can see, I have a line right here and I have work here and work here. I actually did it 2 different ways. I don't think I'm going to solve both ways for you, but I'll describe the second way after we do the first way. And you can tell when you look at my work that one of them is not really superior. It's just a different way to get there, okay? So when you have something like this, a complex numerator linked with a plus or a minus and a single denominator, what you can do is break the fraction apart. And breaking a complex fraction apart is very, very smart to simplify it, because you can then work on individual pieces and try to get it to simplify the little pieces separately instead of dealing with the gigantic thing. So how would you break this thing apart? This would be equal to tangent divided by this, tangent of theta divided by the secant squared of theta, the plus sign because of the plus here. If it was a minus, you'd have a minus here. And then cotangent of theta over secant squared of theta. Now, you might say, well, how does he know this? Well, if instead I gave you this and I said, hey, here's 2 fractions, add them together, what would you do? You would say, okay, I have the same common denominator. I have to have the same common denominator to add fractions. They're both identical. Great. And then the denominator of the answer has to match one of these, okay? Then, since I have a common denominator, I just add the numerators together. And so that's exactly what's in the numerator. So going from here to here, you know how to do from lower level math. I need you to start thinking about doing the reverse. When you have a complex fraction with a single thing on the bottom, you break it apart. The way you check yourself is just to try to pretend to go backwards and see if you get there. And I just showed you that you do. So you might say, well, this looks more complicated. True. But what I can do is work on them separately, right? What is the tangent of theta equal to? It's equal to the sine over the cosine. Sine of theta over the cosine of theta. But that whole thing is divided by this, secant squared of theta. And since I'm trying to simplify things and trying to get things to cancel, I want to replace the secant with 1 over cosine. The secant is 1 over cosine. So 1 over cosine squared theta. The reason I have a squared here is because really it was secant squared, so I replaced it with 1 over cosine squared. Now this looks complex. The goal here is to try to get things to cancel and to try to make some headroom. You cannot see. This is a proof where, or a problem, I would say. I would challenge anybody looking at this. If they look at the problem statement and tell me that they know what the answer is, they're either lying or they're a super, super, super genius, because there are too many steps in this problem for anybody of reasonable skill to be able to get to the answer. Now, hey, people are out there way smarter than me, so I concede that. But I think most people are going to have to feel their way through the problem, and you can't see it from the beginning. So I don't know ahead of time if this is going to work, but what I do know is it's legal. Because all I did is turn the tangent into this, and I just turned this into this with the reciprocal identity. And then what I'm going to do over here is the same thing. The cotangent is the inverse cosine of theta over the sine of theta. And then the division bar from here. And then the secant squared is the exact same thing, 1 over cosine squared theta. All right, I'm leaving room over here because we're probably going to need the room. This is a little bit of a lengthier animal here. So what do we do next? We have fraction division. We need to do that. So this is going to be sine theta over cosine theta. This division bar will turn to multiplication. We'll flip this over and write down cosine squared of theta over 1. We just flipped it over, multiplied. That's what we got here. Then, similar thing here. Cosine of theta over sine of theta. Change the division to multiplication, flip and multiply. Cosine squared theta over sine of theta. All right, so we made a little bit of progress because here we have a cosine and here we have a cosine squared. So this is going to cancel with only one of them. So that's why I strike through the exponent, leaving behind a cosine. Okay, over here, actually, nothing appears to actually cancel. Let me catch up to myself and make sure, look, I made a mistake already. I make mistakes all the time. Apologize for that. I'm on autopilot. This is over 1. Because what we have here, when we did the division, we flip it and multiply it. So the cosine squared goes on the top and the 1 goes on the bottom. So you should be checking your work. Everyone makes mistakes, including me. I always tell people I make mistakes. It happens. All right, what are we left with? We have the sine times the cosine. That doesn't mean anything or simplify to anything. So I'm going to put the sine of theta times cosine of theta, but there's nothing in the denominator anymore. So it's just sine theta times cosine theta. Notice when we canceled here, we only canceled one of the cosines, so one of them was left behind. And then what do we have here? Cosine, no, this is fraction multiplication. Multiply the numerators. We have cosine cubed of theta, which is weird, times on the bottom, this or over the sine of theta. So this times this is sine, this times this is cosine cubed. Now, this does not look any simpler than this. So at this point, you're looking at it and you're like, okay, maybe I took a wrong turn. Maybe this is not going to work out. And it's true that there could be simpler ways to do this. Absolutely could be. Absolutely, right? But as long as you're sure that the steps you've taken are correct, that they're not wrong, then all the work you've done is not going to lead you in the wrong direction as far as like, you'll be able to recover from it. So when I look at this, I still don't really know if I'm getting closer, but I check my work and I'm like, okay, all I did is replace this with this and this with this and then do the division and the cancellation. I'm reasonably confident this is correct. So what do I do next? Well, I have done a cancellation, which is nice. What I want to do now is to try to cancel things. So whereas I broke the fraction apart here, now after I've done this intermediate cancellation, I'm going to try to combine these fractions back together. The goal by combining them back together is to try to cancel something. I don't know if it's going to work, but that's what I'm going to do. So over here, what we have is the sine theta times cosine of theta. And then way over here, I'm going to put a skip over here and say cosine cubed of theta over sine of theta. How do we combine these together? We need to get a common denominator. And remember, a common denominator, we're going to use sine of theta. Any common denominator will work, but we want to choose a common denominator easier to get, or easy to get. So what I'm going to do is take this term and I'm going to multiply it by the sine of theta over the sine of theta. Notice that this term is just equal to 1, so I'm not changing anything here. But what I'm trying to do is get a common denominator. You know, this is like in fractions and with regular numbers. You can multiply any fraction you want by any number you want, as long as you do it to the top and the bottom. And you could do that to try to get a common denominator. I'm doing the same thing here, but instead of multiplying by numbers, I'm multiplying by sine over sine, which is multiplying by 1, which doesn't change anything, but it gives me a common denominator. So what do I have? This term times the sine, because remember the numerator times the numerator is going to give me sine squared theta, because I have two sines here, times the cosine of theta. And then on the bottom, it's going to be sine of theta. And then over here, it's going to be cosine cubed of theta over sine of theta. Now I have a common denominator, and I can add these together. So what I'm going to do, I think, is I'm going to do it here. I have a common denominator, so I'm going to add the numerators. Sine squared theta, cosine theta, plus cosine cubed of theta, all divided by sine of theta. And you're thinking, oh my gosh, this is not getting any simpler at all. Let's move over here. What I'm going to do is I'm going to recopy the last step. I'm not going to change anything. I'm just going to recopy the last step. Let me catch up and just check myself. Everything's going well so far. I'm going to rewrite what I have. Sine squared of theta, cosine of theta, plus cosine cubed of theta, and then all on the bottom, sine of theta. All right, all I've done is a direct copy of this, right? Then you ask yourself, okay, what could I do next? In the numerator, notice I have a common term. I have a cosine here and a cosine here, so I'm going to factor out a cosine of theta. In that first term, I'm going to have left over a sine squared of theta. And then over here, left over, I'm going to have a cosine squared of theta. And then on the bottom, I'm going to have a sine of theta. Notice if you back multiply, you get this term. And if you multiply over here, you get this term. So I know I factored out correctly. But, drum roll please, anytime you see a sine squared plus a cosine squared, it's always equal to 1. So this whole thing in parentheses is equal to 1. That's a common thing you do in trig for identities and simplifying. Try to get a sine squared plus a cosine squared someplace, and then it disappears, and a 1 shows up in its position. So what we have then is this whole term just becomes 1, and all you're left with is cosine of theta times 1, technically, over the sine of theta. And the 1, of course, doesn't do anything. What is cosine divided by sine? That one is cotangent of theta. This is the final answer. And like I said, I challenge anybody who tells me that they look at this and they already know that it's going to come out to cotangent of theta. Okay, great, maybe it's true, but I'm skeptical, and also I just think, I mean, there are some people out there that can see that I mean, there are people out there that could do this, but they're extremely rare. Most of us just have to take a little step and see. And I'm telling you right now, some of you might look at this and pick apart my solution. And you might say, why did he do that? This would have been simpler. Maybe because I didn't see it. I'm not a genius, okay? But I know that the steps I did are legal. And what you have to do when you're proving or simplifying something, if it's not quickly simplifying, then you just take the next logical step. So let's go through this one more time. What we did is we broke it apart. We got this. Then we replaced everything with a simpler version of itself in terms of the reciprocals here. Then we did the flip and multiply, and we did the cancellation. This is the step that allowed the solution to happen. Once we remultiplied everything out, we got this, which definitely did not look any simpler. You might give up here, but then you say, you know what, let's combine it back. We have to get a common denominator. So we multiply this by sine over sine. Why? Because we were choosing this as our common denominator. This is what we got. Since we have a common denominator, we kept it, and we added the terms in the top. We recopy this step over here, there's no change, and then we say, what can we do? I don't know if it's going to help, but what can we do? I can factor out a cosine only in the top, and then when it hits you like a thunderbolt, this is left behind. When I look at this, I don't see anything simple. But as soon as you pull out the cosine, you see, oh, okay, that's what I'm supposed to do, because this becomes a 1, and then the answer here, cosine over sine, becomes a cotangent. Now, I told you I worked it 2 ways, and I did. What did I do in my alternative way? I'm not going to solve it again, but what I did is I started here, and I did not break the fractions up, essentially at all, throughout the whole problem. What I did is I replaced the tangent with cosine over sine. I replaced the tangent I replaced with sine over cosine. Cotangent I replaced with cosine over sine. Secant squared, I replaced it with 1 over cosine squared. And without, verbally, it's not going to make any sense to say anything more than that, because the steps were just mathematical steps after that. But once I had them all in place, I worked on getting a common denominator for what was in the numerator and combining it all together. And then once you get that giant mess in place and then do the fraction division, some things cancel, and then you get to the same place. I will leave it as an exercise to the reader to do this, or the viewer, to do this problem again. Replace this with sine over cosine, replace this with cosine over sine, replace this with 1 over cosine squared, and then I'll give you a hint. In the next step, try to combine what you have here into a common fraction, and then basically just go through it and then see if you can get it to equal the same thing. It is possible because I have the steps right here. But, you know, it's all about practice. It is. And it doesn't come easy. We have to practice this stuff to get good at it. So I'd like you to look over these fundamental identities and practice with them. You have to solve all of the problems that I'm giving you. Notice some of the identities and problems are very simple. Some of these simplifications are just really, really simple, and some of them are monster. And so it's just going to work out like that sometimes. Get your practice. Make sure you can reproduce what I've done. Follow me on to the next lesson. We'll continue to build your skills.